Thank you, Yossi, for the very kind introduction. I should also thank Ollie because he ended up making slides for this entire talk, and I borrowed quite a bit of them. So thanks, Ollie. So this is a talk about converses for statistical estimation problems. So given an estimation problem, and you come up with some estimator, we'd like to know we would like to know lower bounds on the performance of any possible estimator. So we call it converse here. Okay, so here's the setup. We have some quantity theta of interest. It belongs to some set F, and we get to observe some data y. So let me call it a sequence y1 through yn, and this y depends on theta because it's generated according to some distribution p theta of y indexed by theta. And the question is, how well can we estimate our quantity of interest as the number of samples grow? So let me give you a couple of examples. The first is density estimation. So your set F here is the set of all, say, smooth densities on the unit interval 0, 1. And let's also assume that the set of densities have the set consists of densities with bounded second derivative. And what you get to observe is I.I.D sample from some density in that class, say theta, and y1 through yn are drawn I.I.D according to that density, and you want to estimate the density. And your measure of performance of your sum estimator theta hat, which is a density, is the squared Hellinger distance between your true density theta and your estimated density theta hat. Okay, so this is a loss function that measures the error, if you like, between your estimate and your true value of your theta. Okay, a second example that I'll talk about later is compressed sensing, where here theta is a tall vector of length n, and you get to observe it through a noisy linear measurement. So what you observe is y, which is a theta plus noise, and a is this fat rectangular matrix of dimensions m by n. Okay, and in compressed sensing, m is typically much smaller than n. Okay, and clearly you need some assumptions on theta if you want to do a good job of estimating it. So a common assumption is sparsity, right? So our f here will be the set of all unit norm theta that live in n dimensions with at most k non-zeros. So k is the sparsity level, and here, given any estimator theta hat, we measure our loss by the squared error, or the average squared error between theta hat and theta. And here the question we want to ask is, what is the best possible worst case risk? So if I have any estimator theta hat, what is the worst case risk over all thetas in this set F? Okay, so the set F has unit norm thetas with at most k non-zeros, and we want a nice expression or a lower bound for this worst case risk that depends only on this matrix A. Okay, so here are two examples I'll come back to. So back to the general model, we have theta which belongs to some class F, and we want to estimate it using samples from or using a sample y from p theta of y. And we have a loss function to estimate the performance of an estimator theta hat, and this is going to be denoted by d. So d of theta and theta hat is a loss between theta and theta hat, and we'll assume that d is a distance or a semi-distance. Okay, I'm not going to define what a semi-distance is. You can just think of it as a distance. Okay, so this loss depends on the realization y, and the risk is just the expected value of the loss, where the expectation is taken with respect to this distribution p theta. Okay, so the risk is a function of theta, and what we want is to understand what is the worst case risk over the set F. In other words, we want to get lower bounds on the minimax risk, which is defined as the worst case risk of the best possible estimator. So is the setup okay? So this is what we wish to do, and there's a fairly standard approach to obtaining lower bounds on the minimax risk, which I'll now describe. Yeah. So for details, you can look at this nice book by Sibakov on non-parametric estimation. Okay, so it starts with a very simple Markov's inequality argument. You fix some positive scalar psi n, and then you say that the probability that your loss exceeds psi n is no larger than 1 over psi n times the expected value of the loss. So this is just Markov's inequality, and what you want is the risk which pops up on the right hand side here. Okay, so you just take the psi n to the other side, and then you say that the worst case risk, by taking supremum on both sides, is at least psi n times the supremum of this deviation probability. Okay, so what you want is to lower bound this deviation probability that the loss exceeds psi n, and the supremum of that over all theta in your set. So this set F may be a very rich class. So for instance, F was the set of all smooth densities with bounded second derivative. So in general, this is difficult to compute the supremum of this probability. So what we do is we consider a smaller class, a carefully picked class, and then try to lower bound this probability over that class. Okay? So the class is called a packing set in the literature. So what we do is we take m different elements from the set F. So think of it as m different densities in the density estimation case, or m different vectors in the compressed sensing case. And then we carefully pick this class so that if you take any two elements from this class, say theta I and theta j, the distance between them as measured by the loss function is at least some value d min. Okay, and I'm going to choose d min to be 2 times psi n, where psi n is this number here. Okay, so the good news is you don't actually explicitly have to construct such packing sets. There, in most problems, you can use Gilbert-Varshama bound or the probabilistic method to construct such packing sets. It requires some ingenuity, but people have done it for a large class of problems. Okay, so once you have this packing set, one notices that this any estimator theta hat can be used to distinguish between these m different hypotheses in the packing set. So here's how it works. So you get y, you run your estimator, you get theta hat, and then you map it to the nearest element of your packing set. Okay, you have m elements, and you just do a nearest neighbor decoding, and that will give you an I hat in this packing set. So this is starting to look very much like a channel coding problem, and it helps to think of it that way. So here's the formal connection. So here's a channel with input theta, and output is your sequence y. So p of y given theta is your channel, and I'll write p of y given theta here on to just invoke the channel coding connection, where I actually mean just p theta of y. And the code book that you use to communicate over this channel is theta 1 through theta m, the packing set. And then your transmitted code words is one of these elements of the packing set. And then you observe the channel output, which is being generated according to the channel distribution. And then you have a very specific decoder. You look at y, your channel output, you run the estimator, and then map it to the nearest element of your packing set. And that's your channel decoder. Okay, so what we're going to do is, once we've formulated this as a channel coding problem, we're going to analyze the error probability of this channel coding problem and then connect it to what we want is the risk, or the minimax risk. So here's how we do that. So the nice property of the packing set is that any two code words or theta i's in the packing set are separated by at least d min. So by this construction, the decoder makes an error only if the distance between your theta hat, which is not yet quantized to an element of the packing set, and your true theta I is at least d min over 2. Okay, and d min is 2 psi n, so d min over 2 is psi n. So that immediately tells us that the probability that you make an error in decoding, given that theta I is your true code word, is no larger than the probability that your distance between the true theta I and your theta hat is at least psi n. Okay, because you make an error only if your distance is at least psi n, which is d min over 2. Okay, so now we are almost done. We want to take the soup on the right hand side, which is our quantity of interest. You can also take soup here, but the maximum error probability is usually hard to bound, so we just make do with average error probability. And so this is the average error probability of this channel code over all the elements of the packing set, and you say that that is a lower bound for the soup of this deviation probability. Okay, and if you remember, this is what we used in our Markov's inequality to bound our minimax risk. So you just plug this in here, and then we say that our minimax risk is lower bounded by psi n times this epsilon m. Okay, so all this is standard. This was a fairly quick summary. So what our starting point for this talk is this observation that the minimax risk is lower bounded by psi n times epsilon m. And the connection between these two quantities is that epsilon m is the average error probability of a channel code whose code book consists of elements which are separated by at least 2 psi n. Okay, so that's the connection between these two. So in this talk, we are going to use existing packing sets. We are not going to come up with new ones. But what we're going to do is get new lower bounds on this epsilon m, and hence get better lower bounds on the risk. Okay, so now that we've posted as a channel coding problem, the most common approach to lower bound the probability of error is Fano's inequality. Okay, so here's how it goes. So in a statistical setting, a convenient way to write Fano's inequality is that epsilon m is lower bounded by 1 minus this quantity. Okay, and the key term in this quantity is this average of these m KL divergences. Okay, and the ith term here is the KL divergence between the distribution P of y given theta I and this centroid distribution P bar, where P bar is just the average of the Py given theta i's over I. Okay, and the typical way to obtain risk lower bound is to say that, okay, I'm going to upper bound this average KL divergence. Say I upper bound it by alpha log m, and typically this is the order of bound you can get. And once you get that, you just plug it in here, and what you get is epsilon m is lower bounded by 1 minus alpha times this small quantity, because m is large. So this is nice, and it gives you a lower bound on the risk. But one thing to note is this alpha may be, any constant between 0 and 1, and often it can be pretty close to 1 as well. So this is a weak converse, because it's well known that Fano's inequality gives you a weak converse. And the question is, can we improve on Fano? Okay, so that's the starting point for this talk. And over the last several decades, there have been tons of work on improved converses for channel coding problems. So here's just a quick summary. I'm not going to go through all of these, but you can divide them into a few different classes. You have generalized versions of Fano, including some very recent work by Sasson and Verdu. And then there are other like stronger converse techniques based on information spectrum, sphere packing, generalized divergences, and so on. But in this talk, the approach we take is going to be the one based on hypothesis testing. Okay, so Hayashi and Nagaoka were the first, I understand, to connect formally the channel coding problem, which is a memory hypothesis testing problem, with a binary hypothesis testing problem. And subsequently, in this paper by Polyansky, Poor, and Verdu, they introduced what has since become known as a meta-converse, which is saying that you can lower bound the probability of error of a channel coding problem, this epsilon m we are interested in terms of the type 1 and type 2 errors of a very specific binary hypothesis test induced by your channel decoder, which I'll talk about in a little bit. And in fact, in a subsequent paper, they showed that the Vasquez, Villar, and others showed that this meta-converse is actually tight if you optimize over the parameters involved. Okay, but the meta-converse in general is not computable. So what we want is actually a lower bound for our statistical estimation problem, and we want a bound that's computable for a wide range of problems for which Fano has been used, and even for those for which Fano potentially cannot be used. So we want to use existing packing sets, and we want a bound that we can easily replace Fano with, and that gives us a strong converse. In other words, it gives you epsilon m tending to 1 as m grows, which basically tells you for large n, this is the best possible lower bound you can get with that packing set. Okay, so that's the program. So here's how we do it. So let's recall our channel coding problem. The code book is induced by the packing set, theta 1 to theta m, and we want to lower bound the error probability of this channel code, epsilon m. Okay, so the first step is to observe that any channel decoder defines a hypothesis test, a binary hypothesis test, to distinguish between two hypotheses. Okay, the hypotheses are H0 and H1, and H0 I call, so the hypotheses describe a distribution for this joint pair theta y. Under H0, theta y are jointly distributed as p theta times qy. Okay, that means theta and y are completely independent. P theta is just the uniform distribution with weight 1 over m for each of the elements of your code book, and qy is some distribution you can fix, but it's independent of theta. So your H0 is the hypothesis that theta and y are picked independently. H1 is the hypothesis that they are jointly distributed according to the channel. So first you pick theta uniformly from the code book, and then you pass it through the channel, and then that's how you generate y. Okay, and this hypothesis test is actually very simple. So what you do is you have a pair theta y. You want to decide if H1 is true or not. What you do is you take your y, pass it through the channel decoder, you get some decoded theta, and just compare it with the theta you already have. If it's the same, you say H1 is true. If it's not, you say H0 is true. Okay, this is a silly and simple hypothesis test, but it turns out to give useful bounds, a converse. Okay, so if you exactly analyze the type 1 and type 2 error probabilities of this test and relate them, you get the meta-converse, which we don't want. Instead, what we do is something simpler. Okay, so before we go there, a simple calculation will show you that your type 1 error probability, that you make an error when your h naught is true, is actually 1 over m. Okay, because when your h naught is true, these two are independent and they look as if they came from the channel only if you pick a particular code word. So that has probability 1 over m. And your type 2 error probability, it can also be shown that it's epsilon m, your channel decoding, the probability of error of your channel code. So once you have these two, we relate them using the simple inequality, which has the type 1 error and the type 2 error on the left hand side, and this scalar gamma, which is a positive scalar, which we'll optimize over later. Okay, so there was the E gamma divergence mentioned in talk yesterday, and if you maximize the left hand side, you optimize over the best possible test, binary hypothesis test, the left hand side is actually equal to the E gamma divergence. And so this inequality says that this left hand side, which is a combination of your type 1 error and the type 2 error, is no larger than the probability that your likelihood ratio of P over Q is greater than gamma, and the probability under the P distribution. Okay, so now all we do is we take this hypothesis test, this Q and P probabilities, and plug them in, and we get this lower bound. You get this 1 over m is greater than 1 over gamma times this. Okay, now the only term that's a bit complicated is this probability term of this likelihood ratio. So what we do is we use a Markov inequality type argument, and then we bound it in terms of Renyi divergences, and then you get a nice expression over gamma, which you optimize over all gamma, right? So after all this, what you get is the following result. We get that epsilon m, the average error probability, is lower bounded as 1 minus this expression. So let's parse this a little bit. This has a scalar lambda, which is any scalar that's positive, and it's also in terms of qy, which is any distribution we fix to specify the h naught hypothesis, and it satisfies some mild conditions, which I'm not going to go into. Okay, and then on the denominator you have this m term, which is the number of elements of your packing set raised to the lambda over 1 plus lambda, and then you have this average of exponentials of these Renyi divergences. Okay, so the ith term in this average is the Renyi divergence of order 1 plus lambda between the distribution P of y given theta I and the qy. Okay, so remember the qy is anything you can pick, and the Renyi divergence is defined as, of order 1 plus lambda, is defined as 1 over lambda times log of the expectation of this likelihood ratio raised to the 1 plus lambda. Okay, so now the point is, how useful is this? So it should be computable. That's what we care about. Okay, so what you need to do in order to compute this is to pick a good qy first, and then fortunately there are often nice ways to upper bound the Renyi divergence, okay, depending on the problem. So you pick qy, and then you have to calculate or bound the resulting Renyi divergence, and then there's also the matter of picking lambda. Often you can just start with something simple like lambda equals 1, but you can get tighter bounds by optimizing over the scalar lambda. Okay, so in this paper we use this result, this converse result, to study 3 illustrative examples. The first two I already mentioned, compressed sensing and density estimation, and I'll talk a little bit more about them in the rest of this talk. We also apply it to a third problem, which is the active learning of a binary classifier. So I won't talk much about this. You can see the paper, but maybe I'll just mention what the problem is, because it's different from these two in the sense that the learning process is active. So what you have in the third problem is that you have d-dimensional vectors which are either labeled as 0 or 1. So these are feature vectors which have labels 0 or 1, and what you want to find is the optimum classifier, which is in d-dimensional space. It is some region, it's some curve separating the space into 2 regions. Okay, and what you want to find is the curve. And in active learning, what we are allowed to do is we are allowed to give examples, and then an oracle will tell us whether it's 1 or 0. Okay, we can give it a feature vector and it will tell us its label. And active learning means that you can generate each example or each feature vector depending on the results of the past. So which means you can probe the boundary of the classifier and learn. Okay, so this has some interesting connections with channel coding with feedback. I'm not going to talk about them, but you can see the paper if you're interested. So what I'll do in the rest of this talk is focus on the first two problems and show that you can get improved bounds, essentially with the same packing set constructions that other people have given. You can apply a result to show that epsilon m tends to 1, which is a strong converse as opposed to Fano. Okay? Right, so here's back to compressed sensing. Recall that what we have is a linear model. We want to recover theta from measurements of the form y equals a theta plus w, and w is Gaussian noise. I'm going to assume with I.I.D. Gaussian noise with variance sigma square. And the class of theta we are interested in is unit norm vectors with at most k non-zeros. And what we want to lower bound is the worst case risk, which is the expected mean square error over this set. Okay, so the first thing to do is the packing set. So the whole space of vectors we're interested in consists of unit norm vectors with at most k non-zeros. So Candace and Davenport constructed the following packing set, theta 1 to theta m. So they pick m vectors such that all those vectors have unit norm, and then they're well separated in the sense that if you take any theta I and theta j, two different vectors, the square distance is at least 1/2. Okay? And then they also have this nice property that that the average of these outer products is very close to the identity. Okay? I'm not going to talk much about this, why this property is needed, but it's needed for some of the calculations they do. Okay, so the point here is the second property is the most interesting, that these are well separated, and they show using the probabilistic method that you can construct a packing set of size at least n over k times k over to the k over 4. So this is exponential in k log n over k. So this is a packing set they've said exists using the probabilistic method. We're just going to use it, and let's try to compute our Renyi divergence. Okay, so our Renyi term is our lower bound is this, and to calculate a Renyi divergence we first need to fix qy. Okay, a py given theta is fixed automatically by the problem. So py given theta I is just Gaussian with mean vector a theta I and variance sigma square. Now qy, the most natural choice is just to choose it to be have zero mean and the same variance. Okay, because it makes computations easy, and why not? So we do this and we get we can calculate the Renyi divergence. We get it to be this constant times the norm square of a theta I. Okay, where theta I is some element of your packing set. Now this is not directly useful because remember we haven't explicitly constructed the packing set, so we don't have any control over this a theta i's. Okay, unless we assume some properties for a. We don't want to do that. So what we do is we take the packing set and take a smaller subset of it. So remember the packing set had m elements where m was exponential in k log n or something. We reduce its size by a factor of log m and construct a smaller set p, and we show that this p has an extra nice property that this a theta I is bounded over that p. We show that the maximum norm of a theta I square is upper bounded by the Frobenius norm square of a over n times something that's close to 1. So now this gets rid of the dependence on theta I, and so now we are in business, we can just plug it in. Okay, so once you do that, what we get is an explicit lower bound on the error probability of our channel code. So this is 1 minus some terms times log m and m to the minus delta and lambda and all that, where these are scalars. And when you plug it in, you get a lower bound on the minimax risk. Okay, so this is a non-asymptotic bound. So to make it a little more insightful, let's take k and n to be large and see what we get. So our m star a, our minimax risk, is lower bounded by this quantity. So let's parse this. This first term here is like a signal to noise ratio. So sigma square is the noise variance, and this Frobenius norm of a square tells you how much signal power you have in your observations. And then you have this k over 4 log n over k, which if you're familiar with compressed sensing, this k log n often comes up. Okay, in comparison, Candace and Davenport used directly the packing set with the Fano based argument, which requires some detailed computations, but what they get is the same bound, except that they have around a factor of 8 worse in the denominator. Okay, so you want a larger lower bound. Okay, so one comment is that for this particular problem you cannot improve more than constants, because it's known that, for instance, for certain a which satisfy things like the RIP, this k over 4 log n over k times divided by this Frobenius norm square is the best you can get. So there's achievable estimators that get this within constants. So you can only improve up to constants. Right. So in the last, I guess I have 15 minutes. I don't need as much, but in the last few minutes, what I'm going to do is also show you an application in density estimation. So in density estimation, our set F is a set of all probability densities on 0, 1, which satisfy two properties. One is our density is bounded between A0 and A1, and the second property is that it has bounded second derivative. And what we are given is y1 through yn generated I.I.D from theta, and we wish to estimate the density using some estimator theta hat n, and here our loss is going to be measured by squared Hellinger distance. And this is just because we are building on loss functions and packing sets used in previous work. And what we want is to obtain a lower bound on the worst case performance of any estimator. Okay, here again we need a packing set, and this was constructed by Bin Yu, or building on examples even earlier. So the idea is you take the uniform density on 0, 1, and your packing set is going to be densities which are small perturbations of the uniform density. Okay, and these perturbations are going to be defined by some smooth function g, which integrates to 0 and has some finite second moment. So the idea is you partition the interval 0, 1 into m different subintervals. So I think it might be easiest to draw this out. So what you do is you have the interval 0, 1. This is 0 and this is 1. This is the uniform density, and you partition this into subintervals of width 1 over m. So there are m of these, and this is the uniform density. On each of these intervals you either perturb it by some scaled version of g or minus a scaled version of g. Okay, so in particular you define in the jth interval, I define this gj to be a scaled version of g restricted to, say, this is a jth interval, this is gj, and then I just perturb this density by this much. Okay, and in each interval j you can either choose plus gj or minus gj. So what this leads to is what's known as a hypercube class of densities. You get 2 to the m densities because you can perturb each of these subintervals by either plus or minus. Right? So each density is indexed by some vector tau, which is a plus minus 1 vector of length m. Okay, in subinterval j you perturb by either gj or minus gj, and m will be chosen. It's going to be something large. Right, so the way we choose our packing set is from the hypercube class of densities. We first say that I want sequences of length m which have pairwise Hamming distance at least m over 3, and this is guaranteed by the Gilbert-Wassermann bound. Okay, so there are 2 to the m sequences in this minus 1, 1 to the m, and Gilbert-Wassermann bound tells you that there's exponentially many sequences, a subset of sequences which are separated mutually by at least m over 3, and then you take the densities corresponding to those sequences, and that's your packing set. Okay, and for that packing set it can be shown that the Hellinger distance is at least this. It falls as 1 over m to the 4. Okay, so it makes sense, as your m increases your dmin decreases. Okay, so now once you have that packing set, which is all done for us, in this case it turns out to be convenient to take qy to be the uniform density, and let's take lambda equals 1, and then our Renyi divergence becomes fairly straightforward to bound. Okay, so this is of the form e to the n over m to the 4. Okay, and remember we want this term to be very small. Okay, so you plug in all this, so you take m equals n to the 1/5, and so what you get is that your minimax risk for this density estimation problem falls as n to the minus 4/5 times some constant times epsilon m, and now our epsilon m is 1 minus 2 to this exponential quantity. This exponent goes to 0 as minus n to the 1/5. Okay, so bin uses the same method, packing set, construction, and Fano. So this gives you a weak converse. So this epsilon m, she shows that it's strictly bounded away from 0, but it does not go to 1. And the method also requires some restrictions on the constants involved in the densities. So again, we get constant order improvements, but it's also known that there exists achievable estimators getting this n to the minus 4/5 rate. So here also, constant order improvement is the best we can do. Okay, so that brings me to the end of the talk. So in summary, what we did was obtained lower bounds on the minimax risk of statistical estimation problems using a packing set argument plus a lower bound on the average probability of error of an induced channel code. The packing set was all, from previous work. The only contribution here, you can say, is a way to use a lower bound on the channel coding part of it that gives you a strong converse as opposed to Fano, which gives you a weak converse. But it's nice that you can, wherever Fano has been applied, it seems that you can apply it without much effort. And as I said, there's another example in the paper. And I should remark that very recently we noticed a paper which gives you small improvements over the main theorem. Some of the constants, the lambda stuff, can be improved a little bit. In the future, it will be much more interesting to see if, instead of just improving constants, whether we can get improved minimax rates as well. So for problems in which Fano is either difficult to compute or doesn't give you the optimal rate, can this Renyi divergence type argument give you an improved rate? And there's also work that instead of using explicit or implicit packing sets, you can just work with global metric entropy features. So for many problems like density estimation, the metric entropy of the function class is known. So can you extend these techniques and replace Fano in those kinds of settings? Okay, so with that, I'll stop. Thank you.
We have time for about 27 questions.
Yeah.
I like it. Okay. More like an intuitive one. So because in a way you have like this estimation problem, right?
Yeah.
And then you relate it to a channel coding
Yeah.
problem, and then you use a converse bound that goes back to hypothesis testing, right? So my question is, couldn't you maybe do this directly, like going directly from the estimation to like a hypothesis testing, which is somewhat closer, and sort of lose the intermediate steps, which might give you something tighter?
Yeah, that's an interesting question. Yeah, it's not clear how to go from a statistical estimation problem to directly a binary hypothesis test. I think there's Aswad's lemma, Aswad and Lecam's method, which they use some kind of binary hypothesis argument. I don't remember it exactly, but I think those tend to be useful for a different class of estimation problems. But yeah, that's worth thinking about, I guess. I don't know.
I mean, even if you follow exactly the same approach as the Polyansky, Pourverdue, and so on, right? I mean, you might even just mimic it and see whether you can go directly. Right?
Well, I think the problem there would be, remember, what you're trying to do is bound the soup of this deviation probability over a very rich class, and the reason we map it to a channel coding problem is that we carefully pick this big subset, the packing set, that in some ways is not a very bad bound for the probability over the rich class. I guess it's intuitively, to me, it's not still very clear why the meta converse gives you a good, a tight converse for the channel coding problem. It's just something, right? So
yeah.
I guess that needs to be understood a bit better. Yeah. Yeah.
Maybe one thing in common, because you mentioned Hayashi for the
Yeah.
hypothesis testing. I think the idea that you use hypothesis testing for converse bound goes even back to Shannon, right? It always sounds like Hayashi was always the first to come up with the stuff, but I think already Shannon himself thought about hypothesis testing in Playhood later and so on, right?
Yeah.
I'm not very good at literature, but I think these are
Yeah, but this is specifically binary hypothesis testing, right? Yeah. Yeah.
There are no more questions. I guess we can.
Yeah.
There is one more question.
Okay, I have a comment,
Yeah.
sort of a question, but a comment to the comment. I did some thing with region estimation and hypothesis testing, and there the connection is more clear. And I'm kind of wondering. So in the talk that you gave now, it was very clear why you had this packing set. But now at the end of the talk, I'm confused again why you have it, because we didn't need that. We didn't do that at all. But of course, our problem was region estimation. We weren't trying to do a point estimator. And so,
I see.
And the connection there to hypothesis testing for region estimation is more binary hypothesis testing is more clear, but maybe this sorts out the question of why you can't just jump.
Yeah, I mean, I guess as you said, the reduction to the packing set comes because we want the soup over this entire rich class. So instead, you can think of it as we try to compute a soup over a well-chosen subset, and that becomes a channel coding problem. But still, in my mind, it's not entirely clear why the channel coding problem is the converse of it is well captured by a binary hypothesis test. Ollie, do you have any thoughts?
No, not particularly.
Yeah. But as I said, maybe the Aswad and Lacam methods, I think they map more directly to binary hypothesis test, and they are to do with estimating functionals rather than the functions themselves.
Yeah, but I mean the Binu paper says that Aswad and Lacam aren't better than Fano, but Fano is as good as them.
Yeah.
And this is better than Fano,
Yeah.
therefore, yeah.